Good afternoon, everybody. Thank you for joining our webinar on AI strategies to address data accessibility challenges in biomedical research. I'm Catherine Farrell from the Division of Extramural Programs in the National Library of Medicine at NIH, and we're excited to host this webinar today. First up, here is today's agenda. Following this brief introduction, we've lined up 3 exciting NLM funding researchers who will present for about 25 minutes each, followed by a brief Q&A session. In the final 20 minutes of the webinar, we will have a panel discussion session where we expect, we'll have a panel discussion session where we expect to, which we expect to be thought-provoking and stimulating. I also want to let you know about some housekeeping items for this webinar. Firstly, to let you know this webinar is being recorded, including all discussions. Secondly, for asking questions, please use Zoom's Q&A feature. Questions will be asked at the designated Q&A time slots. Please note that the chat feature will not be available for attendees, so all questions will be directed through the Q&A feature. Thirdly, we will make a recording of the webinar available on NLM's website early next week, and the link will be sent to all registrants. Here is some background information on the webinar content. The purpose is to explore collaborative strategies for creating high-quality data sets, for reducing expert burden through innovative data processing techniques, and for fostering community engagement and collaborations. We want to share the latest developments in those areas and to stimulate discussions on how shared methodologies can be applied across domains to expand data availability for health research. We're excited to host 3 groundbreaking researchers who work on distinct types of biomedical data, namely electronic health records, biomechanics data, and biomedical imaging data. Each researcher is harnessing the power of machine learning and AI to overcome data accessibility challenges that minimize the need for manual expert intervention in data preparation processes. Their work has resulted in shared resources that can serve as benchmarks to develop, test, and improve computational methods. From this webinar, we hope attendees will be able to gain a deeper understanding of the role of community-driven efforts to overcome data accessibility challenges, and to gain insights into the importance of collaboration in achieving breakthroughs in health research. Our 3 speakers and panelists are Dr. Özlem Uzner from George Mason University, Dr. Karen Liu from Stanford, and Dr. Lee Cooper from Northwestern University. Our first speaker is Dr. Özlem Uzner, who is a professor and the department chair of Information Sciences and Technology in the School of Computing at George Mason University. She will present her pioneering work on extracting valuable information from electronic health record narratives using natural language processing. Welcome, Dr. Uzner, and thank you for joining us today.
Thank you, Dr. Farrell and the NLM team. I'm really honored to be here and excited to share with you the things we have accomplished under NLM sponsorship in the last couple of decades. So thank you for this opportunity. I will try and get into my slides, and please confirm with me when you can see my slides.
We see your slides.
Perfect, thank you. Again, good afternoon, everyone. Thanks for that kind introduction. I am Özlem Uzner. I'm a professor and department chair at Information Sciences and Technology at George Mason University. I'm also a research affiliate at MIT. My research focuses on clinical natural language processing. And for people who may not be familiar, this is the area of unlocking the information that is presented in the narratives of electronic health records, so that we can use them for downstream processing. A lot of the information about patients is in structured data, but there's also significant information about the patient and their care and the rationale for actions that is documented in clinical narratives. Our focus is to extract this information from the clinical narratives, but methods for open domain natural language processing, sort of like news articles, NLP methods, don't apply to clinical notes. This is because it's a very different genre of notes. They are written by the doctors and for people like themselves who have the expertise and domain knowledge to understand these notes without necessarily having to explain it to lay people. So this creates a very different kind of writing style that is very dense in information. It's full of jargon, so you can find notations for disease names, and they can be mentioned in shorthand notations as well as their full names. You can find acronyms that are commonly used in the domain. You can also find notations like SOB here is shortness of breath, but of course it's obvious to the doctor what they mean, so they don't need to write that. They can just write SOB. When it comes to understanding and automating the understanding of these notes, these turn into challenges for us. And also just to note, like for social history section, for example, there is no subject in these sentences. It is assumed that they're talking about the patient. And again, the purpose is for the doctor to just make notes for themselves and for people who are like themselves, who will be involved in the care of the patient. And then they can just take it from each other and continue the care and be able to use that information to care for the patients. If we want to extract all this information from the narratives, say for methods that want to study some statistics in the distributions of various diseases, for example, in a population, we need to make sure we extract the information correctly. So we need to get to the semantics of these notes. That means when we see a short excerpt like this, coronary artery disease and CAD are the same disease. We need to be able to make that connection. We also need to be able to extract accurately that the upper GI bleed here is due to a gastric ulcer. The reason is known. So there is no need to think of these as two independent concepts in the context of this patient. They're very much related to each other. One thing that keyword-based methods would fall short on is looking up things with keywords, for example, like biopsy, Biopsy, if someone is looking for a patient who did not have a biopsy, unless we extract the context correctly that it's without a biopsy in this patient, it's absent, then we would have this patient as a false positive in that sample of patients drawn. So we really need to look at the context and understand what is being said about how these concepts relate to each other. If we can do that, we can open up these notes to a variety of applications. So just to name a few, we can look for patients based on their clinical care documentation, whether they would be good fits for a clinical trial before they even get to the point of needing it, but we can keep them on our radar. Or we could aggregate across all the notes of all the patients in the hospital and use that aggregate information for decision support. If we see a change in the trajectory of the patient, a certain aspect of their health, we can plan early intervention and personalized treatment. So a lot of possibilities and a lot of the information that can support them and strengthen the structured information is in the narratives. Getting to the narratives is the key part of how we start to unlock the information. And I'll focus on 4 challenges to getting to the information, the narratives, so that we can prepare them for downstream use. First is access. Second is availability of gold standard. And then I'll talk about 2 challenges related to the nature of the data. That's variability and complexity. Let me start from the beginning, and this is about access to data. As we all very well know, health data is highly private and it's protected by Health Insurance Portability Accountability Act and various other regulatory processes around the world. Getting to health information is quite difficult. And I'm okay with that as a patient, but as a scientist, I'd like to be able to automate the processes that will make the information accessible for downstream use to improve healthcare, to improve research. And there is value in opening these nodes up for researchers that will help us make sense out of them. Before we started to share data, the access was limited to people who are in-house to that data owning organization. So you would go through the IRB process, get your IRB approved, access data, write your program evaluated on your data. It's great, it works for your hospital and for that purpose. But then the advancement of the NLP field and the methods that open up these nodes fell behind. So, because if person A does it on their own institution's data and person B does on their own institution's data, it's not necessarily the case that they will be able to exchange notes and use the same method on the same data. And they may not even be able to learn the same lessons from each other. So that really limited scientific progress. To help address this gap, since 2006, with some visionary colleagues from Partners Healthcare and Harvard Medical School, we were able to convince the IRBs, starting with Partners Healthcare at the time, to allow us to de-identify records and then to be able to share them with the research community. Well, of course, everything happens with appropriate data use agreements. And if we have this data set, the idea is that we can build a benchmark data set that all the different methods by different researchers can be developed and evaluated on the benchmark data set, helping us identify the state of the art. Since 2006, so it's been a while, 18 years, we've been developing data sets from various institutions. Partners Healthcare was where things started for us. Beth Israel Deaconess Medical Center, through the MIMIC2 project, was already sharing the identified data use data for research, and they participated in sharing their data for our purposes down the road. University of Pittsburgh Medical Center shared some data. Mayo Clinic contributed some notes throughout the duration of our research, and University of Washington, Seattle also contributed data sets. So you can see there has been a trend with the sharing of data sets from 2006 that more and more institutions, and these are just my collaborators, I have to say there are others who were inspired and empowered by the release of data by Harvard and by partners and by Beth Israel, that they were able to convince their IRBs to share data as well. So this is great. We have built some precedents and started to unlock some data sets that can become available for use in research. The second thing is that you can't just get the identified nodes and build all NLP on it. You need one more thing to get started, and that is availability of gold standard. That is the second challenge, and this is a challenge in almost all AI methods. The gold standard is the answer key that you would have experts develop for the task that you're interested in. And then that answer key helps you then develop methods that you can automate the process and replicate human answers. This is very costly and it is very time and labor intensive. So you would need to get to the experts in the task to get them to give you the answers for your task. So in my case, it would be medical experts, and they are very much interested in saving lives as opposed to annotating data. So I'm very grateful to them for their generously contributing their time and energy to this. And there's financial aspect that goes with their experience that needs to be taken into consideration. So you can develop gold standard data sets, you just can't do it all the time for everything, and not everyone can do it. Again, if we have a resource that is shared with the research community and we can all benefit from a gold standard that is generated for the tasks that will advance the field, then we are in much better shape as a field. So we can then compare all the systems on the same gold standard. And that is really the key to understanding the state of the art and what works and what doesn't. So we can move together forward armed with that knowledge. So since 2006, we prepared gold standard for numerous tasks. So that's in the tasks column in here. So it appears twice in the second column and the fifth column. So number of tasks. We split up our effort into two main categories. First, we did in the green, you'll see these are basic NLP tasks. So concept extraction is like finding the diagnosis, whether the patient has it, how do the concepts relate to each other. Co-reference is, can you track an entity throughout the discussion in a note? And temporal relations is, can you create a temporal ordering of the events that happen to the patient, for example? And a couple of others. So these, you can imagine, if you can extract this kind of information from the notes, you can use it for a variety of applications. And our applications are in red. Those are smoking status, for example. If I know that someone is a past smoker, current smoker, or non-smoker, if I am evaluating treatments for asthma, that would give me good context to understand what happened to the patient and how that may have affected, smoking may have affected the outcome. Other clinical applications were obesity and its comorbidities or progression of heart disease risk factors from longitudinal notes. So we share these data with the community through shared tasks. So we followed a process from Open Domain NLP where you split your gold standard data into training and test portions, and you disseminate the training portion with data use agreements to your participants of the shared task, but you hold back the test set. So no one sees the test set that is for evaluation until all development stops. So after a time period, there's a cutoff for when development has to stop and the test data are released to the community, and then we collect results and we are able to see what performs, how well each approach performs. Typically, we have accompanied these shared tasks with workshops and journal special issues. So we had 11 workshops, typically meeting with the American Medical Informatics Fall Symposium, for participants to get together and present their systems, the errors of their systems, the successes of their systems, for a collaborative learning opportunity. And as I mentioned, we had journal special issues. Journal of Biomedical Informatics was a generous host for years, and Journal of the American Medical Informatics Association is a continuing generous host for our special issues that document the state of the art and the lessons learned from the shared tasks. So this remains a resource for the community, but I want to focus on the rest of the talk, the challenges that I see for natural language processing to move forward. We learned a lot over the years from the shared tasks. And I mean, do we have the formula for unlocking the whole field? Do we just go and annotate data sets and share it with the community and we'll eventually get there? Well, maybe, but I think we need to think about that a little bit. One thing that we learned is data, clinical data is different everywhere. And that may be common knowledge to some of you, but I want to show you with some quantification where we found that advancing the field isn't as simple as just build a more sophisticated system. Just whatever you did wrong last time, don't do that, do something else, do whatever the best system did, and you'll get there. Well, it's not like that. One of the tasks that we worked on in the past was de-identification. So every time we had to release new notes, we had to de-identify them. And then because we were de-identifying them manually, multiple passes, that's always a key aspect of it. Then we figured, well, we could also use these to run a shared task and see how the systems are doing. And you expect that if the field is moving forward, we're going to see an upward trend in the performance numbers too. Let me back up for 1 second here. And for folks who may not be familiar with the identification, brief introduction that this is the task of finding 17 pieces of textual personal health information in the narratives for the purpose of removing them, so that it's the first step towards having the notes be considered de-identified for release purposes from IRBs. So names are in that list, ID numbers are in that list, phone numbers, etc. are in that list. So every time we annotated these, we ran the shared task, as I said before. Well, this is the trend that we were expecting, the upward arrow, but we see a trend downwards in the numbers. And you can be sure, going from 2006 to 2016, the sophistication of the system improved, right? So the first one was a conditional random field. And when we ran the identification task, then we got about 98% performance. We're like, wow, we're done. We could just do this all the time. Well, in 2014, we had psychiatric nodes. No, this is longitudinal nodes for diabetes patients. So when you say longitudinal nodes, you have a mixed bag of nodes, including progress nodes and communications with patients and lab results. Well, a more sophisticated conditional random field there performed less accurately. And in 2016 was the psychiatry nodes. Performance went down further, where although the method is now a BIOLSTM, so we went into the deep learning era here, and we expect this number to be higher, but no. Well, there are, of course, things to learn from that. So not all clinical data is the same. And even the same task, when you see the same task on different data, it looks different to the systems. It may not look different to humans, but it does look different to systems because the context in which the key information is being discussed is very different. So for a discharge summary, these are very fact-based notes. So there isn't much storytelling about the patient. It's about the physical system. Talk about what happened to the patient, how their body responded to certain thing, what were the interventions, what were the outcomes. Whereas 2016, it's very different. Psychiatry notes, and people tell the story of their lives, right? So now they're talking about so many different aspects of their lives, other people in their lives, where they work, and the task becomes a very different task. So not all the data are very different. To quantify this, when we were working with the 2016 data, because 2014 was very recent at that time, we said, well, okay, so teams, if you worked on 2014 data without seeing the 2016 data at all, can you apply your systems to the 2016 data? And they did. So this performance went from 94 to 80%. Okay, so like 14% loss. Yeah, you'll get used to that number. It was like, whoa, to me at first, but then I got used to it. You'll see it again. Now, if we use the training and test portions of the same data set, of course, we closed the gap back up. We were back up to 91%, which is a much more palatable number than 80%, right? Okay, well, so this is saying that the notes were in fact different. There is 80%, that is the clinical context that is probably common to them, but there's also difference. So they have differences in the way that they utilize PHI information that came as a loss in the performance. So that's one of my first conclusions that I can quantify. The notes vary from department to department, even within the same institution. These are all the same institution's data. Well, I expect something similar, maybe worse, going from institution to institution. So let's check that one out too. For this one, we used our own in-house the identification system, Neuroner, which is a BIOLSTM CRF itself. And we use data from Partners Healthcare and from University of Washington. So the first row here is University of Washington training data, and then you test on University of Washington test data, 91%. This is comparable to what we found in the partners notes when everything was from the same distribution. Now, if you use the external data set to train your model and you apply it to UW test data, you lost about 13%. So remember I said we're going to get used to that number, 14%, 13%. So there it is. Going from one institution to the other, we lost some in the performance. But this is not all bad, because without having any data from UW, so let's say one institution does not want to annotate their data, or they want to minimize how much data they annotate, they could use existing data from other institutions to give them a jump start, and they'll already be at 80%. Right. So, and if you develop a little bit of ground truth for your own data, that's the concurrent and fine-tuning lines here, you're already going to jump back up to 91%. I have to say here that the amount of training data from University of Washington that we put in here is a fraction of what we annotated. So we had 1,000 nodes, and we could in fact get to the peak performance with 200-300 nodes. So, and you could even beat what you would have in the ideal scenario. So here it's all UW data that you train and test on. But if you started from external data and you fine tune to UW data, we even slightly beat the performance. This difference was statistically significant. So external data does give you a significant boost if you're trying to use it for starting annotations in your institution. The remaining of this table is the opposite direction of the same experiments. The numbers are not the same, but the conclusions are the same. Well, can you just get any external data then to give you a jump start? Well, our UW data was a mixed bag of nodes. We had 100 from each of these types of nodes. And it turned out that of the partners' data sets, the one that worked most commonly is the one that has also a mixed bag of nodes. So this is the longitudinal nodes of diabetic patients, including progress nodes, as well as patient-doctor communications, lab results, and it gave the best boost in general for the UW data set. So the lesson there is, if you have multiple data sets available to you for jumpstarting your annotations, do a few experiments to see which one fits your data the best. You may find that admit notes in one hospital will give you a boost for admit notes in the other hospital, or maybe not, but the similarities in the data definitely play a role. The last thing I want to touch upon is the complexity of the domain. In general, what we observe is that a medical domain has a lot of imbalance in the data. Some of the events that are really significant, like adverse drug events, are rare events. And this is not good for systems that rely on statistics in order to make decisions. I'll show you an example now. And also ambiguity and domain knowledge come into play when we're interpreting the nodes, and systems still lack that level of understanding and interpretation. The task I have here is one for clinical concept annotations in cancer events and relations. So it's an oncology data set, and we're trying to extract the medical problems of the patients. So this is a neuropathy, and location is peripheral, and they were given chemotherapy which caused neuropathy. So I'll skip, in the interest of time, the rest of the detail, but we're trying to find medical problems and drugs with their attributes that define what happened, so whether the patient has it or not, if there's a change in the medical problem, severity, anatomy, duration, frequency, and anything else that is worth noting about the medical problem and how they relate to each other. In this case, among the train, validation, and test sets, we had about 110,000 entities annotated for this data set. It's 500 nodes, oncology nodes, overall 110,000 spans of text that mapped to these concepts and their attributes. If you look at the without pre-annotation inter-annotator agreement, humans do a pretty good job of this. So this is all annotating everything from scratch. Although the distributions of the concepts and their attributes is not great, some are very prevalent, like problem, assertion is right there, present or absent is always talked about, but frequency is not, duration is not. You cannot count on finding those in the nodes. But yet humans are very good at detecting them. They understand those categories very well. They're very consistent in how they extract it, and they agree with each other. only in cases where they are maybe categories that are not homogeneous. The characteristic is basically a catch-all category here. It's anything else that I need to know about this disease. And because it's not such a uniform category, even humans would disagree sometimes. I want to focus on the ones that have low sample sizes. Let's see if systems will be able to do this well as well. Especially now we have zero-shot systems that are very popular. So let's take a look. We evaluated 5 systems. 2 are BERT-based systems and 3 are generative language models. With the exception of GPT-4, everything here is fine-tuned to the training set of the data set. So they have seen the data, and even then, you can see that with sample sizes are lower, then performance is lower. GPT-4 is not really comparable here. It's a zero-shot. It had only the annotation guidelines, maybe 1-2 examples. So it did not perform well. I mean, I put it here just because if people are curious about it, but it's not fine-tuned as the other ones are. So for the categories that had great representation, the systems did well, and as sample sizes went lower, of course, they were at a disadvantage. We analyzed the errors to see what else they may have gotten wrong, and ambiguity is a big problem here, and interpreting the text with domain knowledge in mind. What we found is, especially if you have a bunch of events discussed in close proximity to each other, then the methods would confuse the drugs and the treatments, and they would misclassify whether something is a drug with the duration of taking the drug, or whether something is a medical problem with some other aspect, like characteristic of the problem. So knowledge, domain knowledge, and understanding the context is very important for this ambiguity to be resolved. GPT threw in some hallucinations, but well, we got used to that, so that's okay. And besides, it had no training data. So for going forward, I do think that for NLP, we need to focus on variability of the data and see if we can build more general methods. So getting more data sets out there, more institutions, more data types, more tasks, it's all going to be helpful for that, so we can find solutions that really can benefit the field as a whole. We need to think about data imbalance. So rare events are high stakes events in healthcare, and statistics are against us for developing methods that will capture them. So we need to keep an eye on that, as well as figuring out how to benefit from domain knowledge. Really, experts need to be in the loop with whatever we're doing. At the same time, though, I can say proudly that as a field, with improved access to the data and more people are sharing their data sets, we have improved availability of gold standard benchmarks, and we have understanding of what methods can do well and not so well. And we will keep moving the state of the art forward altogether, I'm sure. In the future, hopefully we'll go into multimodal and other data sets to strengthen our perspective on the patients. I want to thank my generous sponsors, NLM, NIH, and my collaborators. Only a handful of them are named here, but thank you.
Thank you for a great talk, Dr. Usner. So if anybody has any questions, please go ahead and enter them in the Q&A. Let's see. So I don't see anything currently yet, but meanwhile, I'll ask you a question. Like, can you share your thoughts on the balance between data privacy and the need for open access in advancing health research?
Oh my gosh.
What challenges have you come across?
Oh, it is a very tough balance. Of course, I leave that in the hands of the institutional review boards and their comfort level. But our approach from the NLP side has been to be pretty aggressive in what we define as HIPAA categories, and to be able to respond to whatever the IRB is going to allow. So it may be, in one case, they may be able to stomach releasing zip codes. In another case, they may not be even okay releasing dates. Depending on the applications, I think it is worthwhile considering having differentiated approach as opposed to one size fits all. Whether it's all or nothing is not the discussion. In my mind, it is more for this impact, given what it's going to give back to us, how much risk can we take? The risk is for IRBs to decide, of course, but for me, from the NLP side, we're happy to develop methods that will give them that kind of powers that they can say, we can leave the dates, and we have that granularity built into our de-identification that we would be able to cater to that and any other variation that they would ask.
Yes, we have a few questions coming in now. How many clinical notes do you have available overall? And what can you say about using unannotated clinical notes for pre-training?
Is this overall since 2006, or is it related to a specific task?
This is a one of the attendees' questions, so just answer it like specifying.
Oh, I see. I'm not sure I heard the whole thing, but
yeah.
For training or fine tuning, we had about 400 nodes and 600 maybe for testing. We usually do a 60-40 split for training and test, but if it's only fine tuning, we can go less on training side and more on testing side.
Yeah. Okay, and here's another one. Thank you. Wonderful presentation. How does the change of the diagnosis protocol of diseases contribute to the variability of data?
Interesting. So this would, because we are working on the clinical narratives, if we are trying to automate the various coding processes, then it would affect us. But at this point, it doesn't affect the data sets or the methods that we have been developing.
Yeah. So a couple more questions.
I'm not sure that I understood the full meaning of that question, but my best.
Yeah, me too. Have there been any efforts to characterize the errors, and can you provide an anecdotal breakdown of those types? Further, can you compare and contrast those errors of most concern for modelers versus clinicians?
Clinicians don't make mistakes. I don't think I'm supposed to say in a recording anything else. That's a great and difficult question. And I will be able to answer it maybe in a year on a data set that my colleagues from University of Washington released. They have been looking at catching clinical errors from the data set, so like medical errors. Right now, I don't have the medical error side of it to be able to say how the systems differ from the medical errors. I can see in my annotations. So when I showed the cancer oncology data and the annotations that they don't get those wrong. Their understanding of the note, they are in sync with each other. They agree the results are reproducible. So there is no discussion of whether something is a medical problem and something is a cause of it. Whether there are actions taken, if it is going to that direction, that has not been explored yet in the scope of this project.
And we have time for one more question, and that's what challenges or obstacles are there besides the technical side, such as funding or availability of tasks or problems to apply methods to solve?
Yeah, that's another great question. The access to data and convincing the hospitals that the technology can work for them is a great challenge. While there's a lot of value in the notes and in the information, and it can empower both clinical research and care, the purpose of those notes isn't to enable NLP research or the technical research. The purpose is to move forward with the care of the patient. Therefore, for a getting access to the data and getting access to the right places and the technology in the hospitals to be able to build these technologies in a way that is consistent with their workflow. It does not interrupt their workflow, but it supports them, is currently still a challenge. So once we've had the best NLP system, we still need to work with the hospitals to be able to deploy them and use it with them in a way that supports them.
Okay, thank you very much. And we are right on schedule now to introduce the next speaker, who is Dr. Karen Liu. She's a professor at the Computer Science Department in Stanford University. She will present her work on machine learning and cloud-based data processing to revolutionize the biomechanics data field. Welcome, Dr. Liu, and thank you for joining us today.
Hi, hi everybody. Well, thanks for inviting me. It's a great pleasure to be here to talk about my research. First, let me share my slides. Okay, can everybody see the slides? All right,
We can
great.
see them.
All right, thanks. Thanks for the introduction. My name is Karen Liu. I'm a professor at Stanford. A little bit of background about myself. I'm a computer scientist. My research interest is at the intersection of computer animation, robotics, machine learning, and of course, biomechanics. I lead this lab, we call it the Movement Lab. We're interested in studying motion intelligence by recreating or modeling coordinated, functional, and natural human movements for digital agents, and also for real robots interacting with the world. So you can see our research span across many different areas, and the potential impact of our application is also very broad. So if we're able to predict human movements, in biomechanics, we open up a lot of healthcare applications, from sport medicine analysis to exoskeleton design. Studying human motion also has a significant impact in robotics. We can either use our knowledge, our models, to train robots to interact with humans, or train robots to be like humans, to move like humans. And being able to predict human movement also has huge implication in industrial design or ergonomics analysis. 3D human motion is an important topic in character animation and computer graphics. And that's actually how I started this field. Being able to synthesize realistic human motion can improve the fidelity of a lot of the digital humans using VR, AR, video games, and other applications. So in the past, we have been building a lot of physics-based models to simulate human motion. We design motion controllers that determines the muscle activation or joint torques that the agent has to produce in order to generate human-like movements. And so you can think about this controller. This box is where this motion intelligence is encapsulated. It takes as an input a current state and decides what action needs to be in order to create the functional movements. So the models we build can simulate virtual humans to perform complex motor skills that looks very compelling. However, when it comes to predicting the movement of a particular person interacting with the real world, we don't have a clue whether our simulator is in any way reflecting the reality. So one thing we do know is that if we don't consider real world data, our human models are quite useless in predicting real world behaviors. So building data-driven models for human motion predictions has indeed become the mainstream techniques that dramatically change the field in robotics, in computer animation, and now biomechanics. Specifically, in the last few years, we start to utilize generative models, you probably heard of that, learn from motion data to synthesize human motion without the underlying physics models. So for example, the goal of this project is to train generative model to imitate human ability to dance to music. So if we viewed human motion as a similar process of generating language, we can then use similar machine learning tools like transformers, architectures, diffusion models to generate a time series of poses. And in this project, we also make the generative model to be conditioned on the music input. So here I'll show you one example that's a motion that's generated by AI with the music, the audio as the input. Let me turn down this bit. So if you play a completely different music and I able to listen to the music, understand the and you can play music almost any genre. And one interesting thing about this model is that we can edit online. What I mean by that is that in this case, we have animators that determines the lower body motion and play the music and let AI model figure out what the upper body motion should look like. All right, another example here is to synthesize full body human motion from videos. So if I tell you that this is the video on the left side, is the video of the agent is seeing right now, what would be the corresponding full body human motion? And here our result is shown in blue with a comparison to the green, which is the ground truth. And here is another example. So this is an underdetermined problem. We all know there's infinite, possibilities of emotion that you can generate in order to match that egocentric input. And that's why a generative model becomes very necessary for research like this. And here's quickly show another example. The input here is the motion of object. And from that motion of object, we want to know what the person is doing in order to give rise to that, the motion for that object. And our model can do that for a wide variety of different objects, different scenarios. Here is a close-up video on that. So this is the input, sorry. Let me show this again. This is the input to the AI model, and here is what the model thinks the person would be doing. All right, so these are all really fun projects in computer graphics domain. After investigating these generative models for human motion the past few years, we're quite convinced that human motion, like text and videos, have strong spatial and temporal structures that can be learned effectively by generative models. And naturally, the next question would be, if we have a significantly more amount of a human motion data, can we learn a large models for human motion analogous to ChatGPT for natural language? And such a large motion model will serve as the foundation for all applications involving motion prediction. And just like, large language model, when feeding a random seed, it would generate infinitely long human motion that is random, but similar to the real human motion data. We can have the model predict not only the kinematics of emotion, like body poses, but also the dynamic information such as the contact forces with the environment, the internal joint torques, the muscle activations, those dynamic information that give rise to the kinematic poses that we observe. And we can condition this model on practically anything. If you have a data like audio, video, text, and other stuff. If we have a label medical data, we can also condition physiological parameters or biomarkers of a subject. Of course, none of this would be feasible if we don't have training data. Moreover, the training data has to be very large in scale and highly diverse. Think about internet scale the training data for ChatGPT. In the context of a human motion, this training data set has to contain hundreds of hours of a human motion, 3D human motion, and a wide variety of activities in diverse environments. In contrast, the human motion data collection pipeline is designed to collect a small scale data set with only the subjects in the scene and no environmental context. You probably have seen in movie studios or film making process. You probably seen those the motion capture studios where they put markers on the subjects, on the actors, and ask them to move and collect their movements in terms of a 3D marker trajectories and reconstruct a full body motion. So that's the current pipeline for 3D motion capture. So using this current pipeline motion capture techniques, computer graphics and computer vision communities have collected a decent amount of human motion data and share with the public. But the problem of these data is that it only has kinematic information. You only know the poses, the trajectory of the poses, rather than the underneath dynamics, the physics of the motion. So in contrast, biomechanics labs typically are equipped with force plates to capture dynamics information. However, existing biomechanics data set tend to be very small in size due to the labor-intensive data processing. Additionally, biomechanics data sets are highly heterogeneous. They might or might not have upper body motion. They might or might not have IMU or ground reaction forces or ENG data. So in other words, they're just not machine learning ready because the format and everything is different. So we propose a solution, we call it Add Biomechanics, which is a web-based tool that can automatically process raw motion capture data to generate accurate digital twin models and their kinematic and dynamic motions. So just to motivate the background a little bit, this is, if you imagine, this is a landscape of human motion we have today. We have some shared data sets shown in green, but much more unshared data collected by individual researchers or labs. And because Add Biomechanics is fully automated, it can expedite the data processing time from days to minutes, so the researchers can collect larger amount of data more easily and more quickly. And because Add Biomechanics handles this entire post-processing pipeline, the output data are harmonized and compatible with machine learning toolchains. And finally, to promote the data sharing, we let everyone use Add Biomechanics free of charge in exchange for their consent to donate the data. And with this mechanism, we believe that Add Biomechanics can harness and aggregate the data collection effort from every lab or every movie studio and build this unprecedentedly large-scale machine learning-ready data set for human motion. So what is the unique feature of Add Biomechanics that make people want to use them for data processing? I mean, don't we already have a lot of automatic data processing tools provided by those commercial products used by movie studios? And this is a common misconception, I would say. First, the existing post-processing is not automatic for every step. It can easily take experts from hours to days to process a small amount of human data. And second, the current data processing pipeline is incomplete. It stops at generating kinematic motion. A complete data processing pipeline should also include dynamic information, such as the torques, muscle activation, etc. So how do we make the pipeline complete? If we follow the conventional approach, we will process the data step by step, sequentially. And the problem with that is there will be error after processing each stage, and this error will be propagated to the next the subsequent stage and accumulated at the end. So the right thing to do is to consider all the variables at once, right? We could formulate a joint optimization that simultaneously solves for poses, marker offsets, bone dimensions, body mass, joint torques, contact forces, and muscle forces. And this amounts to a large non-convex optimization, which could be sensitive to the initial guesses of decision variables. Previous work has tried many different heuristics to approximate the solution with various levels of success. For motion we know very well, like walking, heuristics can go a very long way. But for less studied motion, heuristics might not work well. Essentially, the technical challenge boiled down to finding a kinematic motion sequence that matches the physics equation exactly. Here we write down the Newton's second law in the Lagrangian formulation. We have two sources of observation from different sensors, the mocap marker positions and the ground reaction force from the force plates. If we plot the center of mass trajectories, we can see that the different sensors will give you a different version of a ground truth. So here the black curve indicates the ground truth. The green curve indicates the center of mass reconstructed from the marker positions. And the purple curve indicates the center of mass trajectory reconstructed from the fourth place information. And you can see that the green curve is closer to the ground truth, and that's the reason why most previous work started out with the kinematic pulses from markers and try to fix it, try to match the ground reaction force as a second step. However, if we look at the acceleration domain, the purple curve appears much more accurate than the green one, because any little noise in the position domain will result in a large spike in acceleration domain. And this makes that optimization very unstable. And since the Newton model is described in the in acceleration domain, we found it much easier to start with a purple curve that agrees with the dynamics and then try to fit the post observation later. So in our formulation, we solve a passive dynamic system expressed as a linear system instead of a quadratic optimization that depends on this very unstable gradients due to the twice differentiation. So this is a secret ingredient, how we reconstruct motion. We can reconstruct both kinematics and dynamics information with very high accuracy against the trade-off between the observed data and physics model. And our method can work robustly across different types of motion as well. Here's more visualization of our results, including joint angles, ground reaction force, and joint torques all being reconstructed at the same time. The quantitative results show that biomechanics can really save days of manual labor, and the results reduce error significantly, both in dynamics and kinematics metrics. Biomechanics has been released for a little bit more than a year, and we have seen a rapid growth in user base and amount of data being processed and being shared. So now we have a really large data set that has a paired kinematics and dynamic information. What can we do with it? So one thing we would like to do is to build a real-time human motion capture system that's portable so that we can collect the data while the person is doing mountain biking or skiing or simply hanging out with the families. And we build this system based on IMU, a very small number of IMUs. We use 6 IMUs for this system. IMU is an inexpensive sensor that measures the linear acceleration and angular velocity at the body part that is attached to. But the information from 6 IMU is not sufficient to reconstruct full body motion. Not to mention that IMU, because it's cheap, usually the signals are noisy, and then the signals would drift over time as well. And this is where biomechanics data set can help. We now can leverage machine learning models, train on high quality data like biomechanics to solve this otherwise underdetermined problem. So here's a result of our real-time mocap systems using 6 IMUs. And my student is, stress testing the system by trying to do something that's completely out of distribution from the training data and see if it will still work. And this year, we take our IMU motion reconstruction to the next level. We want to be able to have a single motion reconstruction model, single machine learning model, agnostic to the configuration of IMUs and agnostic to the number of IMUs. So we want to have the flexibility to decide where to put IMUs and how many IMUs to use on the fly based on the motion of interest without the need to retrain the models for each scenario. So our approach is to train a diffusion model, which enables data editing during inference time, which means that, after the model is trained, we can still edit the results when we execute the model. So we call it, the inference time. And recently, we have seen a lot of application using diffusion model in the image and language domain. The training of generative models starts with a clean image in the image domain, and noise is added to clean to the clean data to create noise image, and then the diffusion model is trained to remove the noise and restore the original clean image. So I'm just going to skip that, the basics of that. But the part we're really interested in is its ability to do inference time editing. So this is a technique known as in-painting. So for example, we can mask the portion of the image we would like to synthesize and provide the rest of the image as input. And during inference time, we simply ask a diffusion model to fill in the mask area, and it would generate a seamless image that harmonizes the input and synthesize parts of the image. Since it's a generative model, we can start a diffusion model with the different random seeds, which results in different output images. Okay, so people have done this routinely in the image domain. How do we take that to the 3D human motion domain? Imagine the image is a sequence of human poses, with each column being a pose at a particular time steps. So we now have an image of 3D poses. We follow the diffusion model framework to train a generative model that synthesizes meaningful human motion from random motion. Okay, now applying the same in-painting techniques, we can provide a motion of an upper body and ask the diffusion model to in-paint the lower body part of the motion. So here you can see that the green bars, the green rows indicate the data that you provided, that the upper body motion, and we want diffusion model to give us the noisy lower body, so that the whole motion will be will look natural and harmonized. All right. So for our project, we will train the diffusion model to predict the full set of IMUs, which consists of 16 IMUs. And each row here is a state of IMU over time. So we have the full set of IMUs during training. During inference time, we can predict the full body motion based on whatever IMU signals available currently, using the online editing and painting tricks. So for example, maybe we only have 3 IMUs attached to the right hip, left knee, and left elbow this time. And we can provide the readings of those 3 IMUs to the diffusion model and ask it to, fill out the rest. And next time you have a different numbers of IMU or different configuration of them, the same model without retraining will still work. And we also want the system to predict motion in real time, so instead of predicting the whole trajectory in an offline manner. So in other words, we want the system to be autoregressive, that can, predict the next pose based on the history it predicted previously. Here are some live demos. The subject first uses 6 IMU to reconstruct the full body motion, and later he just removed 2 IMUs and only used 4 IMUs. And the same model is used in both cases to reconstruct the motion without any degradation in quality. And here's another application using our biomechanics data set. Our goal is to predict the dynamic information about movements from kinematics. Specifically, we want to predict the ground reaction force from the joint angles and joint velocity, which are observable from typical vision-based sensors without specialized biomechanics equipment like a force plate. We represent the data as a time series of vectors, which contain vectors, concatenated vectors of a joint velocity, joint angles, and ground reaction forces. And we train the diffusion model using this biomechanics data set like we talked before. And now we can, once the model is trained, we can ask the diffusion model to randomly generate a motion that looks like this data set. This is what we call unconditional generation. But more interestingly, we can do in-painting again. At inference time, velocity and joint angles are provided as input, whereas the output, the ground reaction force, is covered by noise. And then the diffusion model is used to iteratively generate ground reaction forces that's coherent with the input kinematic information. And this is a result of a ground reaction force estimation. The gray bars here are the ground reaction forces generated by a physics model that's based on a Hahn-Crossley model to compute the ground reaction forces in the software called OpenSim. And the light green bars are the measures the accuracy of the diffusion model using kinematics information measured by the smartphone. So basically it's from a camera, a 2D camera. And the dark green is the same thing. It's the diffusion models that predict the ground reaction forces, but use the motion capture as input kinematics information. And you can see that I think the vertical forces, the vertical force, the normal direction is the most important one. And we can see a lot of improvements already in terms of accuracy in prediction. It could also be used to predict kinetic response to gate modification without performing experiments. This is a very early stage result. It's our pilot study. Previous studies report that large medial lateral trunk sway gait can reduce knee abduction moment, which is associated with a knee osteoarthritis. In this downstream task, we investigate if the model can predict this phenomenon. So we use in-painting again, but instead of using all the kinematic parameters as input, we only use synthetic trunk sway, large trunk sway angle as input. And then the diffusion model generates the remaining joint angles and ground reaction forces that are coherent with the synthetic large trunk sways. Here are the results. This is a baseline trunk sway angle. The range is about 20 degrees. And these three curves, the color curves, are large synthetic trunk sway angles, which is about 2.5 to 3.5 times of the normal trunk sway. And the right figure shows the baseline knee abduction moment, which consistently reduce with the increase of a trunk sway angle. Here we also use experimental data to verify the amount of reduction. And this is what experimental data look like. It demonstrates that we can predict moment reduction simply from the baseline gate. And it takes only 0.5 seconds for the diffusion model to generate result like this, which is pretty reasonable. So this is my last slide. If you are doing research in biomechanics, in human motion, please give biomechanics a try. It's really that simple. Go to our website. You don't need to download anything. You don't need to install any libraries. Just drop your raw motion capture data and wait for a few minutes to get your fitted digital twins and the motion kinematic and dynamic data, motion data back. And I'm happy to, thanks for listening, and I'm happy to take questions.
Yeah, thank you very much for a very entertaining and stimulating presentation. And we've had some nice positive comments on that in the Q&A as well. So we have a couple of questions related to medical conditions. One of them was, can the model be adjusted to account for medical conditions that impact ambulation?
Yeah, so that's a really good question. And that's actually the ultimate goal we want to achieve. Currently at Biomechanics, collect generic motion. Anyone who has motion can donate that. So we're not tagging the data. We're not, building different segments of the data set. So the current state of the data at Biomechanics, we cannot do that yet. But I think that's something that we're working on. We're going to encourage people to donate more specialized data, and then we will be able to do that kind of prediction.
And the other medical condition question was, have you or others considered diagnosing the underlying orthopedic problems and the effectiveness of the therapy based on the patient's gait and posture?
Yeah, so that's a good question. I think that this needs to be done from many different fronts. So at Biomechanics, like a large data set will give us a kind of foundation model or a large motion model that give us a base to predict reasonable gaits based on the conditions. But this is really just a generic model, and it needs to be fine-tuned, needs to be specialized. So, with again, specialized data, we should be able to fine-tune those models and make it more personalized and customized for each scenario.
And Okay, we have time for one more question, and somebody asked, can you also model more fine-grained motions such as facial expressions?
Facial expression, is that hear that word, right? Yeah. Facial expression is it would be great to have that, but it's definitely a different category of data, which means that you needed completely different sensors, different data processing pipeline, and often, and I mean, the model itself is quite different as well. You know, I mentioned that my background is in computer graphics. A lot of my colleagues are working on that problems. It almost feel like a different field, you know, when we go to the facial expression. And another thing to add to that is the physics, underlying physics about face is not as well understood. And we don't have currently we don't have a very good physics-based model for face. And that is also something that a lot of people are working on too.
And just one more final question has come in. Karen, what are the medical applications? Detect disease, predict progression of disease, be a biomarker or endpoint in clinical trials to detect treatment benefit.
Yeah, so I think everything that I mentioned here is something that we would love to be able to support. I think one thing that we really hope to have is to you know, put this in the public domain. Everybody can build their models, and at the same time, I didn't make it really clear in my talk. The reason we're building the portable motion capture system is also try to support the same goal, same vision. We want to be able to people to use their own sensors like iPhones or something very lightweight to collect their data on their own and then use the model to do analysis on their own. And because of that, they don't need to, you know, they can have much faster turnaround in order to, in terms of, you know, diagnosis of their potential condition and disease.
So, okay, so once again, we are now precisely on schedule to introduce the next speaker, who is Dr. Lee Cooper. He's an associate professor of pathology and the director of the Division of Computational Pathology in the Feinberg School of Medicine at Northwestern University. He will present his groundbreaking work on reshaping medical imaging interpretation. So welcome, Dr. Cooper, and thank you for joining us.
Thank you, Colleen, for the invitation and for the nice introduction. Can you see my slides okay?
Yes.
Okay. So I'm happy to be with you all today, and I'm going to be talking about some of the research that NLM has been supporting in our lab. I'm an engineer by training. I've worked on pathology for my entire career after graduate school, and I'm here at Northwestern now, working with the University and Medical Center to see how we can improve, pathology research and practice, through computation. And so what the theme of my talk today is going to be about data labeling, which I think is really the key issue in making AI accessible for everybody. And so for me, this is really an interest of mine out of self-preservation. I'm always surrounded by biomedical researchers who want to apply the techniques that we develop in their work. And we want to move away from a future where, my involvement is necessary to make that happen. And anybody who has tissues, slides, questions can analyze their own data, and preferably in the cloud, and doesn't need to be constrained by on-premises computing resources. So, we really believe that AI should be a basic lab technique for biomedical researchers, just like PCR or Western blot. It should really be something that's, ubiquitous, quick and easy to adapt to new problems. And it shouldn't really require, deep understanding of technical details, and only sort of, understanding basic concepts that we teach on our, first day for our machine learning students here. I think that data labeling is still kind of a key outstanding issue in realizing this vision. And so really, when it comes to developing AI, it's about the data. Many of the other steps can be automated. We have cloud computing now, and so, but labeling the data is still a big problem, and it requires expertise and time and effort. So some of the problems that we're looking at are, how can we identify the best instances to label? So, if you're trying to classify certain kinds of structures, you could go out and do some, brute force approach and just label thousands of things and hope that it works. How can we help you avoid doing redundant labeling, but also identify those key examples that are going to really improve the performance of an AI model? Collaboration and efficient use of skill is another important problem in this field. So, oftentimes in projects we have, pathologists who've maybe worked for 20, 30 years. They're very senior and expert, and, all the way down to residents and medical students. And so how do we direct those people's attention to, the best instances to label that are within their capability, and enable them to collaborate effectively to build labeled data sets. So the last thing is really software and computing. And so I've mentioned cloud computing, but you also really need good user interfaces for data labeling. And there's been a lot of improvement in that in the commercial space and the open source space over the last 4 or 5 years since we started this project. So happy to see that. And we're also doing things to contribute to that. So the context that we're working in is digital pathology. And so, for over 150 years, pathologists have used these glass slides to do their diagnosis. And only recently have they started using digital pathology in the clinic. And so the idea is to take these glass slides and generate digital images. Those digital images will be the primary mode of interaction for the pathologists in the future. And it will create these massive, massive archives that can be used for research. So we have 24 million slides in storage out here in a warehouse in Illinois. Imagine if those were digitized, and to get data to do your research projects, you could just instantly recall those. And so we're talking about really, really large amounts of data. An academic medical center might generate 1.5 million slides a year. That's more than 3 petabytes of data, and that would be year after year after year. So there's really, I think, a potential here to use AI to unlock scientific, diagnostic, prognostic, and predictive value from these images. And data labeling is really kind of in the center of that challenge. So I'll just give you some examples of some of the things that you might want to do, or you would need to build an AI model or do data labeling. So we had a project where we wanted to really map all of the elements of breast cancer and look at the contribution of non-cancerous cells to a patient's prognosis. So looking at cells in their stroma and their immune system, and how patterns of those cells predict a patient's clinical outcome. So currently, when breast pathologists look at a breast cancer specimen, they focus entirely on the cancer epithelium, where the cancer forms and grows, and they ignore largely these other non-neoplastic elements. And so to map, all of these cells and tissue regions in a whole slide image really takes quite a lot of work. You have to build all kinds of models to do that. In this project, we did it in a pretty brute force way. So we built a network of image annotators all over the world and used a web-based platform to collect annotations. We collected 240,000 annotations to train our models. And so, that was a lot of fun, but there's probably better ways to do that. And so that's an example of where, we had a significant labeling problem that went on for a couple of years. In hematologic malignancies, there's examples of really challenging data labeling problems. So here we're looking at a smear of some bone marrow tissue. And so hematopoiesis is very complex. There's a lot of different cell types. And so the questions here are, how does the composition of cell types and their morphologies in the bone marrow relate to, genetic alterations or clinical outcomes? There's a very large number of classes that need to be labeled to build models that can interpret these slides automatically. Some of these things are very common. Some of them are very rare. And so we've had residents working on this problem, and they'll have to go out looking for, macrophages or mast cells and just searching through, centimeters and centimeters of glass, trying to find examples of these things that are actually quite rare. So definitely we need some labeling help in this type of problem too. So in pathology, we have big unlabeled data sets. That's actually a big advantage, I think. Some of the challenges we have are, rare instances. And so again, like I said, if you want to try to find examples of some unique cell, you may end up spending a lot of time just collecting a few examples of those. There are selection biases and redundant instances, like I mentioned before. And also this issue of pre-analytical variability. So, tissues and slides are really optimized for humans to look at them. And so the differences in color don't tend to bother the humans so much, but small changes in color or tissue slice thickness can really confound algorithms. And so when you're labeling, it's really important to know how to distribute your labels in an optimal way to, neutralize this type of batch effect. So I'm going to talk now about some strategies for how we identify these really important instances. This is from a paper that we wrote with a team in the University of Granada in Spain who did, I think, really excellent work. You can read more in this citation here. So the idea was to use some concept called active learning. And so what active learning is, you have a model and it selects its own training data and presents it to an oracle, which is a human expert, who then labels this data and feeds it back in the model, and then the model will update its view of the data. And so through iterating through this process, the model is able to identify examples where it feels uncertain, to show those to the human expert, and then to converge more rapidly, towards an accurate solution. So here we're showing a diagram where we have an optimal but unknown class boundary shown as this dashed line, a model solution, which is shown in black there. That's just the decision boundary of the model. We have two classes, pink squares, blue circles that are separated by this optimal boundary, although not perfectly. And then we have a bunch of unlabeled examples here. And so the way these systems work is typically to look for the best unlabeled examples. And so they might pick examples over here to try to, bring the optimal and solution close to each other. So a lot of this is driven by measures of uncertainty. And so one of the hypotheses we had in our NLM project is that we need to kind of look more closely at different types of uncertainty and how they can help us pick better examples. So, depending on what field you come from, you may have seen this in another name, but uncertainty actually is composed of two different kinds of uncertainty. There's aleatoric uncertainty and epistemic uncertainty. Epistemic uncertainty is a property of your machine learning model. It has to do with lack of knowledge. And so, for example, if you have an area of feature space where you don't have any labels, you would say that you have high epistemic uncertainty in this region. But this type of uncertainty can be reduced by picking examples here and showing it to the model and labeling them and getting some training. We also have aleatoric uncertainty, which is essentially just randomness. And so maybe you have a data set where you've not really measured completely all the properties you need to, and you can't really discriminate perfectly between instances for some examples, like we're showing here in green. And so this type of randomness is not typically reducible by training. So our hypothesis was really that we want to sort of distinguish between examples that are aleatorically uncertain versus epistemically uncertain. And so we developed a Bayesian neural network to do that. You have an image patch that you would like to classify. It goes through a feature extractor, which embeds this image into some high dimensional space, latent space, where the classification is performed. This Bayesian network does some mathematical calculations to identify the uncertainty of every sample that could be labeled and to calculate the fraction of epistemic versus aleatoric. And then we also have an outer distribution detection component in this model, which essentially says there may be things that are highly uncertain, but if they're like artifacts and they really don't look like they belong in the data, we probably want to avoid those. And so that's the model that was developed. We call this focal. We did simulations using MNIST data and to do benchmarking for different active learning strategies. So you can take these images of digits, and if you sort of merge them together, you create highly aleatoric examples. You can corrupt them with noise and create more kind of out of distribution examples. And so here we're just showing sort of the the equivalent, histology patterns that you could imagine, something that has a mixture of normal and cancer, something that has artifact, something that has blur. And these sort of vary in terms of whether they're aleatoric or really kind of out of distribution. So these simulations showed, I think, very clearly that if you use this uncertainty decomposition, you can get in a machine learning model to converge much more quickly into a more accurate asymptotic accuracy. So here we have accuracy on the y-axis and then sampling of and labeling of instances on the x-axis. And our method here is shown in black. Looking at real-world data from prostate cancer, we compared some of the instances that are selected by different selection strategies. So BALD is one that's, I think, very sophisticated and also uses sort of a probabilistic foundation. But we found that BALD tends to pick these really highly out of distribution samples where we have, essentially things that are unclassifiable. There's marker, schmutz, or other things, present. And that's really one of the challenging things about active learning is these selection strategies tend to go after these very odd samples. And so by introducing epistemic and aleatoric uncertainty and out of distributionness as a metric, we can do a good job of kind of picking more informative things and not really frustrating our data labelers. So here is an image of a prostate biopsy core. There's cancer sort of in the middle area here. We have a region of high epistemic uncertainty here, a region of high aleatoric uncertainty here. The epistemic uncertainty also highlights this sort of marker or inked-rich area here that we probably don't want to label, but our out-of-distribution score also does label that. And so by intersecting these D, E, and F, we can really kind of focus our labeling in areas where there's a lot of epistemic uncertainty, but the samples are in distribution and they don't have high aleatory. So another component of our project with NLM was to look at this feature extraction step and how different models might work and improve the active learning process. So in our grant, we're looking at perinatal pathology. And so the placenta is a very fascinating organ. It serves multiple roles. It helps with exchange of oxygen and nutrients between the mother and the fetus. And it also, mediates immune response in a way that I think is very fascinating too. And so there's not a lot of public data on placenta histology. And so if you want to build a model, you kind of have to roll your own. And so this is really, I think, a good application for active learning. So what I'll show you on the next couple of slides is looking at classifying kind of fundamental tissue regions of the placenta. So this feature extraction step that I mentioned, where you embed these images, is really a critical step. And there's a lot of different ways to do that. So when we started the grant, a lot of people were using models that had been pre-trained on natural images. And so you've probably heard of ImageNet. If you use this ImageNet encoder and you embed a bunch of labeled placenta regions into your latent space, you don't really see any separation between the different classes. So when we started our project, self-supervised learning, which is a technique that sort of builds specific encoders from unlabeled data sets, it was just kind of becoming popular. And so we thought maybe this is something that needs to be looked at in the context of active learning. So what this does is it takes unlabeled data and it tries to align views of this feature extractor for corrupted versions of this data. And the process of doing that lends to really learning discriminative characteristics of the images without requiring someone to come in and label things. So there's a lot of models that have been published, including in the journal Nature on this topic. It's a really hot topic right now. And so we looked at one of these, which is from Faisal Mahmood's lab. It's just a fantastic paper. And this is a model that's trained on 100,000 slides, again, with no labels, but also with no placenta. And so when we look at the sort of latent space of, different classes of placenta tissues using this feature extractor instead, you see very, very good discrimination, which is, I think, quite remarkable. So that's really exciting. So we looked at comparing, ImageNet encoders versus this UNI encoder that I mentioned based on self-supervised learning, and there's really no contest. So we trained active learning by doing queries with different numbers of labels, and you can see the accuracy when you're starting off with this self-supervised learning is quite high already. And it grows to a high accuracy with a small number of labeled instances. Okay, so I mentioned software before. I'm going to take just a couple of minutes to kind of talk about the applications we're building to sort of really enable people to take advantage of these technological advances. And so we have a tool called Resonant Act that we're building that's supposed to sort of serve this active learning platform for people working with digital pathology images. So this is built on a tool that we developed called Digital Slide Archive, largely with funding from the National Cancer Institute. This is a web-based viewer. And so it's something you're supposed to deploy in your data center where it can directly mount your very large digital pathology data sets. It's not something that runs on your notebook computer. And so this would be connected in with, cloud compute or cluster computing capabilities. It can also be deployed in the cloud on EC2 and S3. And so the idea is to have this web-based interface where you can link to large data sets and also have like really strong, powerful backend computing. And so this is something that's been pretty widely adopted in our field. And it was a good starting point for kind of developing a labeling application. So we really worked on customizing the user interface with biweekly meetings with our pathologists. They just come in and say, we like this, we don't like this, move this thing around, call this something else. And I think it ended up with like a pretty refined product that allows people to sort of look through the predictions of models and really quickly refine labeled data sets and really find those key instances that are critical to improving performance. It also allows our attendings and our residents to work together on machine learning projects. So the residents can go and do a bunch of labeling, and then the attendings can come in later and just kind of review and make sure that everything's correct. And so this is still a work in progress, but you can download it and use it. And we're hoping to, I think, have a really complete finished tool by the end of the year here. So part of this software effort is really being able to enable multi-cloud deployments. And so, like I said, cloud, I think, is really essential for accessibility. Not everybody has a powerful computer or a cluster, but everybody can access the cloud. And so active learning, I think, works really well in this environment. You have kind of bursts of computing that you need. So if you're going to search for some instance, you're going to apply a model to thousands of slides. You have to scale up your cluster really quickly, and then at the end you want to shut it down really quickly so you don't have to pay for all that computing. And so this active learning workflow, I think, really fits well with a cloud deployment. So we've done a lot of work on trying to efficiently use storage and GPU resources in the cloud, trying to help people make their research dollars go farther. For example, when we started the project, we really struggled with doing feature extraction on these slides, and we've gotten a significant speed up just by optimizing software and using some of the inference technologies that are available now. And so now we're focused on using Terraform, which is a technology that will allow us to not implement this for each cloud provider, but have one cloud implementation that can be mapped to these different cloud providers. So I'll just leave you with a summary here. I think, over the trajectory of my research with NLM, I've seen that accessibility to AI is really improving, and there's more work to do. But many steps of developing AI models can really improve. I think this labeling thing is really going to be the last thing to fall. And improving the labeling experience and the efficiency really involves a combination of work in theory, human-computer interaction, and attention to software development, like I've shown today. Some, I think, exciting outcomes of this research that are very generalizable is that decomposing uncertainty can really improve this labeling experience by avoiding these weird artifacts and also give you a much more accurate model more quickly. Also, these highly discriminative large SSL models that are trained on really, really big data sets, I think, will significantly reduce the labeling requirements for everybody. It's going to really kind of change this paradigm of active learning, I think, pretty significantly, and that will accelerate AI adoption as well. So just I'd like to thank some of our trainees and our collaborators. Of course, thank you to NLM who's supported us through the years, and I'm happy to take your questions. Thank you.
Thank you for that talk, Dr. Cooper. So please enter your questions in the Q&A for any attendees who have one. In the meantime, there is one question has come in. Right now, patients are generally not able to see imaging results in their EHR. Can you imagine some way to use AI to compress the data files or something that would enable patients and their caregivers just to be able to see their images and or to decrease the size of the imaging data or make it machine readable so that it can be translated to a common format compatible with EHRs?
Yeah, so I think there is some kind of modest AI that's used to, for example, discriminate background from tissue when the slides are scanned. And that's already yielded, I think, really big improvements in image compression. So, we don't, image some of the background regions at full resolution. There could be more opportunities to look at image compression. I think you can get diminishing returns, though. I think, it's probably not going to be a factor of 2. It might be a factor of, 10% or 20%.
Yeah, I'm just, so currently okay, well, another question just came in. Thank you. Charles Barr asks, how much work has been done on correlating pathology features and findings with clinical status, genomic or other biomarkers?
A lot. This research field has grown tremendously, and there are people working in all of those areas. When I started doing this, it was really a handful of people, and 20 years ago, and now it's become quite a large field. So pretty much for any type of disease you can imagine where pathology is done, you'll find some prognostic model or some correlation between histology and molecular biomarkers or other biomarkers. And so I think that's an area where I think we really want to kind of enable pathologists and scientists better, is that they would be able to do these correlations themselves, because there's so many of those studies to be done. I think they have the best knowledge about the significance of what should be done and should be the ones, I think, kind of driving that forward.
Okay, so at this point we are like probably ready to do the panel session. So if we can have the other two speakers join us, that would be great. And if any of the audience has questions, continue to answer them in the Q&A feature. And if you want to direct to one of the particular speakers, please list it in the question too. So okay, so this is a question that, to ask all of you, and you can each comment on it. In what ways have your projects had to adapt to the changing landscape of technology? And what emerging tools or technologies are you most excited about?
I could start. I think, our project started 4 years ago, and just looking back, I think it's remarkable the progress that's been made. I think the biggest area is these large self-supervised learning models. And I noticed that the other speaker, Dr. Liu from Stanford, mentioned that as well. That's been a big impact on our field. It's not something that we saw coming. I think it seemed very implausible at the time because of the amount of data involved, but it's going to really transform, quite a lot of things for us.
I'll just add on to that. I agree completely that the biggest change that I've seen in the last 5 years is probably this generative models or family of a generative model. It started with the GAN many years ago. It kind of worked, but super hard to train. So it's not that useful to us. And then you see the improvement over the years with the VAE, with the now diffusion models seem to take over, at least in my field, and then continue to improve, every day. So that's something that surprised me and pleasantly in the last few years.
Yeah, I agree. It's been phenomenal development in the last few years that we have a lot of the things that were end goals for our tasks are now starting points because the generative models give us a really good start at addressing them. I think so there's great potential for moving faster, further, faster with generative AI models and what they provide as the basis for our starting point. So there's a good side to it and there's a challenging side to it. So the challenging side is that the baselines have all moved. So now starting point is the output of LLMs, and the research questions are, what can you do with them that you couldn't previously do? And then, I move the field further forward faster.
So another generic question, how do you envision the role of machine learning and AI evolving in the next 5 to 10 years within your particular area of health research?
I'll just throw something out. I think I imagine, I don't know, it doesn't take a lot of imagination because I know a lot of people are doing that now. They're just trying to build the large X model or the foundation model for whichever domain they care about, and then they figure out a way to leverage LLMs, the language, like the embedded space of that to make the training even more efficient, and also gather a lot of information and domain knowledge just from the existing LLM. So basically build their specialized specialized large foundation model and figure out a way to leverage LLMs, the existing LLMs.
I think on the NLP side of things, we may see more partnership, human AI partnership in many different aspects of healthcare that's going to come from the developments in large language models. We use them more and more. I think they will probably become more accepted as we understand them better. So right now they're black box and we have issues trusting them, but I think over time we will figure out those weaknesses and address them, and the human AI partnership will strengthen and probably get to the point of care. 5 years, maybe not, but maybe 10, maybe faster. I don't know. It's been moving very fast and we did not see that coming. So it may be sooner than we think.
Yeah, I would say we used to struggle to achieve, I think, meaningful performance on problems that is clinically meaningful, and that's not really an issue anymore. So what I would like to see, I guess, is more validation of these technologies in the real world.
Yeah.
That's really where their value needs to be proven. And just like with clinical trials, you can't just do something in a mouse and expect it's going to work in the real world in humans. So I would really like to see, more people deploying models, tracking their performance, understanding, how the experts like to work with them, what are their shortcomings, how much does all of this cost? I think that's a new frontier for us.
Yeah, that's the next 5 years.
Yeah. So some questions about like interdisciplinary collaborations. Could each of you reflect on the importance of interdisciplinary collaboration in advancing data accessibility, and what steps can be taken to foster such collaboration?
Some things don't exist unless they are interdisciplinary. They're by definition in the combination of the fields. So for people whose passion is to use theoretical methods for applied the results, it seems like a natural path.
Yeah, it's very important. It's sometimes quite hard to, I think, in our field of pathology, the pathologists, they really have their own kind of language that sometimes I think even the clinicians don't understand so well. And so, it just takes kind of a willingness on both sides to, meet in the middle. But that's, I think, for me at least, the fun part is always learning new things about, what other people do.
My, personal experience in working with collaborators from different fields always starts with building a tools for them, because I'm a computer scientist. We build tools, we build computational tools. And at the beginning, it's never very interesting. I'm not interested in their field. They just want a tool from me. But once you start working together, we can find common interest, and then the collaboration becomes more genuine, right? Like we're genuinely interested in each other's field, and that's how I get into robotics, how I get into biomechanics. So I think you have to start out with something concrete.
Like it seems like the understanding of the domain is critical, regardless of the type of quantitative methods one uses. So how can we better train our quantitative scientists in health or medical sciences for this, to prepare them for the future?
We need to talk to them more. I think everyone is just in their own research area and going with the momentum of what they do day to day, and we don't realize the opportunity that if we just talk to each other, we can help each other so much. So it's challenging to break into those circles when they are really going with the momentum of what they're doing, and understandably, I totally understand why they're doing that. But I think AI training would be beneficial to incorporate into the healthcare training. And to include that as one of the building blocks of their skill set, their interface with the technology, how to benefit from it. It would be beneficial down the road, but getting started with that training is probably the challenging part. Just interrupting current momentum is tough.
I think there's a lot of good material that teaches clinicians and biomedical researchers about AI, but there's not a lot of good material for engineers, computer scientists who want to learn about these fields. And so that's where I see a big deficit. And they're just fundamentally different. To be good at biology, you just have to learn 1,000 facts and memorize them. And that's very different from the sort of, I think, mathematical and technical fields that we have, where we have, axioms and things like that.
Mm-hmm.
Yeah, I think that's a really accurate observation from computer science department. It's very, I'm genuinely interested in other fields, but I cannot see the same thing for my students sometimes, because they have a lot of their own interests in their PhD degree, their jobs, a lot of other obligations and things that concern them. So that's how I see why this is hard. I cannot say, okay, just pause for the next, year or so, learn this new field, and then come back to AI. I don't think that's very persuasive to students. So oftentimes I found that if you have a good data set, then the students are interested, they're listening. So if like biomechanics, for example, not all my students in my lab are interested in that, but once you get it into a machine learning ready data set, they become interested to learn more and try new algorithm on it. So you can use a data set as a bait to see as students.
So related to that, what advice would you give to new researchers or startups looking to contribute to the creation or sharing of high quality data sets in the biomedical field?
If they can find a de-identified data set, then they can start annotating the end clinical task. So that helps a lot, because de-identification is sort of the invisible task. You can't do anything without it, but it's not necessarily the NLP task itself. In our case, if it's de-identified, you can just focus on the actual clinical use case and generate a data set quite easily. So one of the things that we decide to do over the years, instead of de-identifying data, which was a lot of time and money as well, to de-identify, just use the same de-identified data set over and over for multiple annotations, and then that gives you a much more comprehensive data set and different challenges each time. So focus on the end task and minimize the de-identification that needs to be repeated over and over.
I would say make sure you understand the nuance of the problem. Talk to the end users for whatever tool you're developing. It all starts before you start doing anything with the data. Analyze the problem. And also, think about disparities as well. I know, that's a big issue that's coming up a lot in diagnostics, and often data sets are riddled with all types of problems that will lead to, disparities in models and tools.
Yeah, I agree. Nothing to add.
And so this common question is kind of an extension of that. Somebody said it's hard to keep data scientists in academia if an industry is so tempting. What keeps you in universities, and how do we keep the next generation?
I wouldn't judge people if they went to industry. Everyone needs to be happy where they are.
Yeah.
So if their heart is there, that's okay.
So I will wave the flag for our universities and say we have the data and the expertise. If you want to work with the world's expert in some biological process or disease, they're most often working in a university. And I think that's what keeps me engaged, and that's something that we have that's very attractive.
Yeah, I agree with that. And I want to also add that if you're in the university, you can still work with industry. You can still have a lot of collaboration with them, use their resources. But the other way around is more limited, right? They have to work with the agenda of their corporations. So I would say one thing that I wish we could have as much as industry, that's the compute. That's really a limiting factor and become more and more so nowadays. And to the point that where we just can't train large models, and we have to use whatever large models that were trained by, by the big tech companies. And that would be something that, to think about, if we could all work together and with the NIH and other agencies to have our own training capability that's affordable for small labs, not just the big universities.
Yeah, I agree with that. But we do have the flexibility to choose our own goals, choose the research problems that will advance the field and that are close to our heart, as opposed to addressing the industry priorities. So that part is also very appealing. So finding a good research question, it's all on us where we want to focus our energies and what's worthwhile solving. That's the big appeal.
Yeah, I'll add one last thing, which is, stability is nice, right? As a career, industry kind of grows and shrinks. And I think there's also a lot of joy in mentoring people and helping to, create the next generation of leaders. And certainly there are opportunities to do that in industry, but I think the way it unfolds in academics is different. And, that's another nice thing that we have.
Yeah, so there's a couple of data sharing related questions for you. One is like, what are the ethical considerations that come into play when creating and sharing data sets? And how do you address them in your project?
Yeah, I think this is a little case by case. Like my case is a little bit different because the data we collect, or we still require people to de-identify it, but it's not much to scrub, right? Because it's really just some like 3D coordinates in time series of 3D coordinates. It's very hard to identify the subject from that. But I think when we move to more specialized data sets with tags, with the text associated with it, then I think a lot of things that discussed by other panelists will become very relevant to us as well.
Data use agreements are very important too. The identification only goes so far, but people need to agree to use the data in a certain way and to do good with it. Some institutions I know now are wary of justifiably of large language models and the use of their data with large language models, it could be a violation of their data use agreement. So it's very important, I think, as a researcher, to read those very carefully and to use data in ways that is allowed by the institution. They still own the data. They're only allowing use for research. So it's important to pay attention to those.
Yeah, I don't have anything to add to that.
Okay, so there's another generic question about data sharing. What, if any, role have general recommendations, for example, fair, findable, accessible, interoperable, reusable principles played in the creation of reference data sets? Or do you see a future, like, do you see any problems with that for your particular area? Especially, you know, how it could become interdisciplinary, how you could make your approach more generalizable.
Yeah, I'm not sure I understand the question. So if anyone can, start, be helpful.
I mean, one thing I'll say is we have challenges in releasing data to the public, and so one approach we've taken is to add value to public data sets by annotating them. And so that's one way that we've dealt with that challenge. And I think, there's a very nice journal, that the name is escaping me at the moment, sorry, GigaScience, that publishes, large curated data sets. And I really appreciate the rigor and thought that they've put into the requirements for documenting everything. There's other data journals that focus on data as well that do that. So, yeah.
Yes, so there's one more question in the Q&A. Alison Dennis asks, is it possible that in the future whole body movement could be personally identifiable with better AI models? So that's probably directed at Dr. Liu.
Yeah, that's it's possible. I think it definitely double-edged sword, I guess. We want a motion to be as realistic as possible when we reconstruct that, but at the same time, it could become identifiable. And then I think when that becomes the reality, I mean, even now, for some cases, it's probably reality already. We might need additional guardrail around it. So the donation and yeah, actually, I don't have a good answer to that right now. The potential issues that we will have to think about it. We probably can learn a lot from other domains like images, videos, right? Those are RGB data that are, very identifiable already. How do they handle, thorny problems like that? I think we can learn a lot from that.
Yes, so let's wrap up now. Like, we are coming up on the top of the hour. So I want to thank all of you for coming today and sharing all your insights, especially in this panel session, as well as all your very stimulating talks. And thank you to all attendees in the audience for listening and contributing today. As a reminder, we'll send a link for this webinar recording to all registrants sometime next week. So once again, on behalf of NLM, thank you all for contributing to an insightful and thought-stimulating session. We hope you all have a very pleasant evening.